So today we'll be presenting our CS225 final project in this presentation. Initial goals. So we had a Bitcoin user trust rating data set, and a sample of it is shown on the right. So the information in the data set was the source, target, rating, and time, and those were used to form the edges of our graph. And in the sample on the right, each column matches up to the source, target, rating, time, respectively, and each row is an edge in our graph. So our leading question is to gather general information about the users. With this, we can find communities within the user base, find the optimal transaction path between users, and rank the most trustworthy users. What we accomplished. So we use DFS to find cycles, which represent communities formed by people interacting the most. We use Dijkstra's algorithm to find the least trustworthy paths or transactions, and the PageRank algorithm to rank users' trustworthiness and find the most active users. Our outcome, we successfully accomplished all of our goals.
So to go over some of the implementation that we used for our graph, since our data was given to us in the form of user IDs, which are numbers, we just decided to use an adjacency matrix. One issue that could potentially happen with this is that there's a lot of gaps between the users' IDs, but since the data set wasn't too large, storing that didn't pose an issue. And then we also implemented some other auxiliary storages of data to help with the other algorithms, like vector of booleans for users, stuff like that.
There are three main algorithms that we implemented to achieve our goals, and the first one is DFS. The goal for this algorithm is to find cycles, and each of them represent communities formed by people interacting the most. This inherits from iterator, and there are like three operators. The subcyclic paths were causing infinite loops, so we had to discard them. For the performance, we decided on splitting cycles into two. One is complete and the other is partial, because for large data sets, we it was required to do massive search over existing paths, and this was taking over 3 hours. For efficiency, this was our implementation. We kept track of the cycle path length and path weight, and the output can be printed in a TXT file, and the user can decide on either to print complete or partial paths. There are two fundamental files. The first one is cyclic graph iterator CPP, and the other is the H file. And the important part of this implementation is to use stack. Here is a high-level overview. We can see that we first get the initial node and then mark as in stack. We find all the connected nodes and we check if edge is visited. And if the cycle is found, we push it onto stack. And we continue as we mark the visited path. This is just like a high-level overview. And continuing to this, we do the iteration by checking if edge is visited or the vertex is on cycle. If we determine that the vertex is on cycle, then we mark this as partial path. We also check for the infinite loops, because of the reasons I explained before, and we sort the path into cyclic vector, so that for printing reasons, we inverse the order as we pop from the stack. The second algorithm is Dijkstra's. The goal for this algorithm is to find the optimal transaction paths, which gives between users, which indicates the union of least trustworthy users. We again inherit from iterator class, and the issue with this algorithm was to change the graph structure. So we mapped the we had to map negative values to positive ones. So we added +1 to each weight. And then we kept track of visited nodes, path length, and path weight. The output is the complete path information and total distance for each shortest path. And we put in an output txt file again. There are two fundamental files, shortest graph iterator CPP and the H file. The essential point here is to use Q. And here's an example. This is again the high level overview of this implementation. We check if the node is not visited. We add weight every visit, mark node as visited, and then we mark them as the best until we find a better one. We enqueue edge vertex, and at the end we compare total weight, and if found less, then we ultimately mark that as the best path and mark all connected edges unvisited. We use recursive implementation here and also use DFS and BFS iteration here as well.
For our final algorithm, we implemented PageRank to rank the trustworthiness of the users. So the basis for this algorithm is we use a Markov chain with the initial state of pi0, which gives each node an equal probability, and matrix P, which is built from the graph. And we have an alpha value, which helps measure the differences of the weights of the nodes from one iteration to the other. And we iterate through the Markov chain until for a designated number of times to get a good enough approximation of the final probabilities. So a quick high-level overview of our implementation. First, we build the Markov chain, as said before, with the equal probabilities, and then we do a designated number of iterations. I think in our final result, we use 100. And then we can sort the probabilities in order to get the final ranking of the user's trustworthiness.
Okay, so for test cases, we were heavily inspired by the MPs because we use catch and we also try to make incremental testing. But in some cases, for example, the graph class, it wasn't possible because we needed to implement like add edge, add vertex before we could test remove edge. We also tested in small files first, like for example here, sample1.csv, and then we tested on the large files, for example, the original file, Bitcoin OTC.csv. And also we divided the test cases in parts so we can test each different algorithm or implementation separately.
Here are some challenges that we encountered. First, for error handling, for incorrect input file formatting, we had to use catch, and we compared data size with edge size. If not equal, then we created a warning. For the large data set iteration difficulties, like I said, for DFS, we created partial and complete path printing. For taking care of the infinite loops, we only included them as partial, and we mostly try to discard them. For non-existing input from the user, it was causing segmentation fault. So we thought that we could give information to the user beforehand, and we've done it by implementing a user-friendly interface in the main file. And for the testing part, we started off with smaller sample test cases, and this also let us debug it in an easier way.
And finally, the gaps in user IDs that was mentioned before, we most notably in PageRank, there had to be special care to avoid taking or calculating for those non-existent nodes. So we had to keep track of what nodes are actually present in the graph and take that into account in the implementation of PageRank.
Before we talk about the conclusions, we want to demonstrate, we want to run our program first to show the output. here we can see that we have no warnings or errors, and we created this user-friendly interface. So it gives all the information that the data set has, and then we input our file, and then we create the output file, and we put 4 options. We can go with finding the rankings, and then we choose the number of iterations. They start with a smaller one, and then we create the alpha. We enter the alpha, and here you can see the output here as well. It was pretty quick, and the first user is 35, which indicates the most active one.
Conclusions. So our project allows users to gather general information about any Bitcoin trust rating data set, and users can build their own crypto communities. So this is done by linking the most active users together, which builds trust and inclusivity. And we can also find the best transaction path between users. And this is important because building communities creates an effective platform for communication and opens opportunities for blockchains and a wider use of Bitcoin. I think this is very important because I think that Bitcoin can reshape the financial industry, which makes our project even more interesting to work on. Just a summary of what Bitcoin can do. It's a transparent and decentralized currency that fiat money cannot provide. Also, there's no middleman, so there's no transaction restrictions or fees or limits on the sizes of transactions. And this leads to an overall more efficient transaction system for financials.
Yeah, and so I think one thing that all of us learned doing this project is the importance of the initial design decisions that we make. Thinking back to the graph class implementation, while the adjacency matrix was definitely the easiest way to implement the graph based on our data set, there were some hurdles we had to design around when working on the later algorithms.
I agree with Chris in the way that you need to decide the implementation. I was in charge of the test cases, and I realized the importance of having like public and private functions, so you can test what you really need and also have more incremental testing.
And personally, looking based on the small run that I made, I can also say that I saw a relation between the most active users and the small communities. The people who are most active are also in those cycles as well. So we can see the relation between like trading data and the interaction, and the it's really important to understand this data set, and I feel like we accomplished our goals at its best. And this is the end of our presentation. Thank you for listening.